Okay, well, let's get started. There might be some stragglers, but they can always chime in. So we're very lucky today at the Center of Astrophysical Surveys to have a real expert in survey science. Professor Isobel Hook is visiting us from Lancaster University. She's been doing survey science essentially her entire career, beginning with work on the Isaac Newton telescope when she did her PhD at Cambridge. She then moved to Berkeley, where she worked with Saul Perlmutter and other members of the Supernova Cosmology project on what would become the Supernova Legacy Survey. She developed the instrumentation of the Gemini GMOS spectrograph, which we're still using for a lot of our surveys today. And she's a member of the LSST UK consortium, as well as one of the experts on the EELTs. But today she'll be telling us about two of the surveys that she's been working with even more closely recently. Foremost, where she's PI of the time domain aspect, TiDES, and the Euclid Space Telescope, which just recently launched. And Isobel, please take it away.
Thank you. Thank you very much. So I hope the microphone's on. Yes, thank you. Well, it's a great pleasure to be here. Thank you very much for the hospitality. It's been a fantastic visit so far. I've been working with Gautam for quite a while, sort of remotely and indirectly, so it's really nice to be here and have a bit of time to talk about these amazing projects that are coming up. So I thought I'd start with just show you where I've come from, if I got the right button. There we go. So I've come from Lancaster, which is here, quite close to Manchester. Most people have heard of Manchester United, so that seems to be the closest thing that in the area. So not that far from the Lake District and Scotland. So, please do come and visit us sometime. It's a very nice part of the country. So I'm actually on a sabbatical visit now. For this year, I'm on sabbatical, and I'm visiting here and a few other places in the US for a few weeks, and then I'm hoping to come back for longer next summer to Berkeley for a while. So this talk, I'm told that there's quite a few supernova people, cosmology people in the audience, and those that aren't will have heard lots of supernova talks in the past, so I'm going to go very quickly over the introduction part of this. So I'm sure you know that the basic issue that a lot of people are concerned about now is this huge mystery of why it is that in the history of the universe, at some point not that long ago, the expansion of the universe began to accelerate. And we know that from observations of distant supernovae, but we still don't know why it's happening, and it's a huge mystery. So there's a lot of effort going into trying to understand this now. So as Gautam mentioned, I've been involved in this for a long time, and I joined the Supernova Cosmology project, which was the group led by, well, actually originally led by Rich Muller, but later by Saul Perlmutter. And this is a picture of the group in 1991, which was before I joined, a few years before I joined, and they were using the Isaac Newton telescope in La Palma, which is actually the sort of connection, as Gautam mentioned, that's the reason I got involved in it, because my supervisors were also using that telescope for another reason. So that group, as you may know, originally was setting out to measure the cosmic deceleration, because most people believed at the time that the universe was spatially flat but contained only matter. And if that's true, you would expect a deceleration rate, but there were problems with that the masses being measured from galaxy clusters particularly were coming out too low to explain the flatness of the universe. And so there was this big mystery, how much matter is there? And you would get to that by measuring how much deceleration there is, or how much gravity is pulling the universe together after the initial Big Bang. And of course, the big surprise was that they found it wasn't decelerating at all, it was actually accelerating. And this is one of the main results, a Hubble diagram showing the peak brightness of type 1a supernovae against redshift. And when you plot the distant supernovae here, you can see just by eye that they are fainter than you would expect for the model which has matter only, which is the second from the bottom of these curves. So that was the big surprise, and particularly if you believe the universe is flat, which we pretty much did because of the CMB measurements at the time, that really means there has to be something else that's not matter in the universe that has this effect of pushing the universe apart and making distant things fainter than you would expect. So that implies some other component, and about 70% of the energy density of the universe has to be in that component to explain these results. And when you put that together, that implies an accelerating expansion. And this was also found by the other group, as we call them, the competitors. It was quite an exciting time, but I won't have time to go into that. And of course, since then, there's been lots of progress. So that was about 40 distant supernovae. It's soon, after a few years of very hard work with major surveys like Sloan Digital Sky Survey, the Supernova Legacy Survey, which I was involved in, and there was also the Essence Survey, which isn't shown on this particular graph. This sample got up to hundreds, so up sort of 740 in this particular plot. And you could start to measure things like not just the density in matter, but also the equation of state parameter of the other component, which here we're calling W, which is the ratio of density to pressure. And by measuring that, the idea is you could really start to understand what this other component is. If the other component is the cosmological constant, which is the simplest explanation and works mathematically, then you would expect W of exactly -1. And right from the beginning, when people started to do these measurements, W was indeed coming in at around -1. So the supernovae themselves on a plot like this give you quite a large, poorly constrained region, really. But when you combine with another constraint, for example, from the CMB, in this case shown in green, the overlap region shown in grey, there is quite a tight constraint. So when you have these more than one type of data, then you can really start to do interesting constraints. So it's the complementarity is really important with other facilities, with other techniques. And then if we go on a bit further, so this is one of the most, I think, the most recent compilation of lots of surveys. There are now 1,500 supernovae 1A on here. This Hubble diagram is on a log scale, so it looks much more linear. And the same things, we're finding the same things. So W, again, in combination with other techniques, is coming out very close to -1. And now the errors are getting smaller and smaller. We're down to about 2% or 3% uncertainties in W, assuming a flat model or with some other data combined. Here I've just tried to put everything on one graph. It's not very nice. It's sort of stretched, but you can really see how well all these different measurements are now agreeing. We've got excellent agreement. We're all finding W of around -1 with about 3 to 6% uncertainty now, depending on the survey. Consistent with the cosmological constant explanation, but we don't understand the cosmological constant explanation, because that implies a vacuum energy density everywhere, which just does not agree with any natural energy scale that you might expect. And I think it's fair to say we just still don't really know what's going on. And I think there's still a big push to understand W, to really measure it carefully, see whether it changes with time or in any direction on the sky, in which case you would immediately rule out the cosmological constant, and it would have to be something more exotic. So that's really what's driving us. And then one other last bit, well, a couple more bits of just a quick introduction. I think one of the main things we've found as time has gone on and we've got better and better data is that it really matters what type of host galaxy these supernovae are exploding in. And for some reason, there seems to be a correlation between the brightness of the supernovae and their surroundings. And that's what's shown here. This is one example, and there are lots of plots like this. But if you plot data from all these various surveys here on a plot of their intrinsic brightness after making some standard corrections that we always do to do with the stretch, the width of their light curves and the color, and you plot that against the local color of the host galaxy that they're in, you can sort of see it's quite a subtle effect, but the ones in bluer local regions of their galaxies tend to be, if I get the right direction, fainter in this plot. And it's just characterized here as a straightforward, just to divide the sample in two, and one side's brighter than the other. But probably there's something more subtle than that going on. But we don't really understand this, but it matters, because obviously as the universe evolves and redshift changes, probably the population of galaxies is going to be changing. And if we don't correct for this sort of thing, we're going to get the wrong answer for the cosmological parameters. So we have to make corrections for this type of thing. It's quite often done in terms of the mass of the host galaxy, because there's a very similar correlation with mass with the brightness of the supernovae as well. But I think it's also fair to say we don't really understand what's going on there. It may be caused by dust properties in galaxies being different. But whatever it is, I think in the future, as we go forward and we make better measurements of the supernovae, we also need to measure the host galaxies. And that's one of the things I'm going to be talking about quite a lot. Right, last little bit of introduction is, we've talked about measuring W. It is possible that W, the equation of state parameter, changes with time in the universe. And so quite often it's parameterized in this way, that W has a constant component and a redshift-dependent component. And again, we've got big enough samples to start to be able to measure these extra parameters. And I've just listed a few examples here. So if the dark energy is just the cosmological constant, then W naught would be around -1, and WA would be 0. And these are the sorts of constraints we're getting now. Big uncertainties, but basically still consistent with those cosmological constant numbers. So here's an example of the sorts of constraints. Supernovae on their own, quite large error bars, but when you combine with other things like the CMB, you get much smaller constraints. But still quite large uncertainties there, and that's an area of where I think the next generation telescopes will really help. So one thing I think we need to bear in mind when we're talking about the changes with redshift, I'm skipping through. Let me just get to this point. So first of all, I think as we go forward, we're going to keep using supernovae. They are a very good way of doing this sort of measurement. We're at the point where statistical and systematic uncertainties are comparable. So as we go forward, we have to make not just larger samples, but carefully control the systematic effects, including things like studying the host galaxies. And our goals are to test, is W really -1 everywhere and at all times? Is dark energy spatially uniform? Does it vary with redshift? And the redshift point I just wanted to make here, again, I really like this plot from Adam Rees. It's quite an old plot, but he was just showing that for the same data set, what would you conclude about how W changes with redshift if you either assume that W varies following that formula that I showed you before, or you just let W be a free-form function of redshift, which is shown by the blue. So this is really just showing that with the same data, you could really fool yourself into thinking that you know how W varies with redshift, but actually you don't really. There's a lot of, well, basically it's completely unconstrained above redshift 1 at that time. It's slightly better now, but I think that's the way to do these plots, really let W vary completely freely, because we don't really know how it should vary. Right, that's the end of my introduction. Let me get on to what's happening next. So I think most of you will know about the Rubin Observatory, which is a major new facility that's coming online. The beauty of this is that it has a very wide field camera, and it will do surveys of the sky every few nights, or the observable sky from where it is in Chile. And that's obviously ideal for finding anything that changes or moves. So for transients, it's going to completely change everything. I think we'll have at least 100,000, that sort of order of magnitude, well-measured Type 1a supernovae out to around a redshift of 1. And we'll be finding vastly more than that. It's just which ones we manage to get onto a Hubble diagram. And this all depends on the survey strategy, which is still a bit up in the air, but these are huge numbers. And it will allow us to do things like break the sample into different directions on the sky and how it depends on redshift, and test things like is the dark energy, whatever it is, isotropic and homogeneous. But spectroscopic follow-up is going to be a big bottleneck. And typically now, we've been following individual supernovae one at a time to confirm their type with a spectrum and get a redshift from a spectrum, and quite often look at the host galaxy as well with a spectrum. But we can't possibly do that for every single object here. So this is a big concern. So there's various ways we can go about this. One is to try and do things without a spectrum at all, but whatever happens, you're going to need some spectroscopy to at least train what you do with the other ones. And this is where this TiDES survey comes in, which stands for the Time Domain Extragalactic Survey, which I'm currently the PI of, but it's a rotating position, so someone else will be taking over quite soon. And this is the survey is going to be carried out with the foremost instrument, which is a very highly multiplexed multi-object spectrograph. And what you're looking at here is the focal plane, which has 2,400 fibers, optical fibers. And so you're looking at the ends of the fibers, which are illuminated here. And the other ends of the fibers go into 3 spectrographs. So what that allows you to do is take spectra simultaneously of up to 2,400 objects. So this is the sort of thing you need for very large follow-up programs. So this instrument is going to do a survey of the southern sky over about 5 years, but it's not actually for transients, it's for all sorts of other science. It's going to be doing galaxy surveys, following up clusters of galaxies and so on. And it turns out that the rate that the supernova part, the sort of rates of supernovae aren't quite high enough for us to make full use of all these fibers. So we're going to piggyback on Foremost as it surveys the sky for other reasons. So as Foremost looks around the sky, everywhere it looks, once LSST is running, the Rubin Observatory, there will be live transients known just because Rubin's going to find so many. So everywhere Foremost points, there will be at least, probably of order 5 or 10, maybe a bit more, live transients in the field of view. So we will move some of these fibers onto the position of those live transients and get a spectrum. So we're going to do that. We're also going to do, in every field, we will try and get redshifts of supernovae that are old ones that we know about but have since faded, so aren't live anymore. But we can still get a redshift of their host galaxy, and that's very useful because it means we can put them on the Hubble diagram, at least get the x-axis of the Hubble diagram for those objects. So that's the basic idea. So we'll obviously miss a lot of supernovae with this. We're not going to be pointing everywhere. There'll be lots of supernovae going on in fields that Foremost isn't pointing at, but over 5 years, and because LSST finds so many, we will build up a large sample. And we're designing the survey now, and particularly one of the issues is we really would like to try and follow where LSST points as much as possible. Right now, we're not officially allowed to point the telescope, to drive the pointing of the telescope at all for our survey, but we would like to at least get in the right area of sky. So just to... We are not... we've always been a piggyback survey, so we are not allowed to say we want to go there, even if we know... So one of the big issues is that Rubin Observatory is considering doing declination strips to get higher cadence on certain areas of sky. If we don't do anything, we are quite randomly looking around the sky. We could quite likely be in the wrong declination strip for that year and completely miss all the supernovae. So that would obviously be very bad. So we want at least some coordination at that level.
So what is driving the... Are you going to get to that? Or what is
Not really, no. It's just whatever comes out the most efficient way of tiling the sky for all the other surveys.
Okay.
So it's just whatever. It's pretty random. And so there's no real downside for them to do what we would like to do. And I think that's the discussion that's happening now. So this is a bit of quite an old map of where the LSST main survey area is, but it gives the general idea of where the overlaps with Foremost will be. This is also quite an old map from Foremost, but you get the general idea that where the overlap is, there's a very large area there, something like 13,000 square degrees. So when you build up that over many years, you build up more and more supernovae that TiDES will get a spectrum of. So this is a really nice animation from Chris Frohmeyer showing with those previous survey designs, which aren't in these declination strips, that as LSST moves around the sky, so does Foremost. So that kind of happens naturally just because there are parts of the sky in our right ascension range that's obviously easier to observe at any time of year. So some of the coordination happens naturally. But this just shows how many days since LSST last looked at a field, each part of the sky is color-coded that way. And so you can calculate, you can't really see it here, but you can work out how often TiDES will visit a field that was observed recently with LSST. So we hope that by doing this, we're going to build up a large sample of all types of supernovae. Of course, we won't know what they are when we point at them, but we expect this is what we'll get. But what we are going to do is just pick everything that's brighter than 22.5 magnitudes that comes from Rubin, and that gives us that's about as faint as Foremost can go. It's only a 4-meter telescope, so that's really what limits us, and that gives us this density that I mentioned of, say, around a few tens per field. And similarly for the hosts, we'll go to about 22nd magnitude in the main survey and about 24th in the deep drilling fields. So what we expect to get out of that, when you add it all up over 5 years, is something like 35,000 live transient spectra. And this is a breakdown of the different types with redshift. So type 1a will probably be the dominant type out to around a redshift 0.6, but starts to fall off after about 0.4. And this is useful for lots of things. Obviously, we could do type 1a cosmology with the type 1a's, but we can also use it to do all sorts of transient rates, demographics. But we can also use it as a training sample for all the ones that we missed. So this is quite important, and I'm not going to have a lot of time to talk about that, but we can use this as a training sample for example, machine learning tools that can do classification of transients just based on their changing light curves. And again, I mentioned the cosmology. And this is a predicted Hubble diagram that Chris Frohmeyer and Maria Vincenzi have put together. This will be published in a paper by Chris coming up. So we've got again on a log scale, simulated live type 1a supernovae where we've got a classification spectrum. Actually, put the numbers as well here. So there should be about 20,000 of those, we think, with a good spectrum. And about at least 10,000. This number I still don't quite understand why it's lower than the other one, so I need to come back to that. But many, many host galaxies as well with redshifts, which will go a little bit further in redshift than the live transients. But for those, we won't have a classification spectrum. So for those, we need to get the classification from the photometry, but using the redshift from the host galaxy that we've got from TiDES. And as well as that, there are some AGNs. So there's another part of TiDES which I really won't have time to go into, which is an AGN reverberation mapping program, where you also can use AGN as standard candles, and or distance indicators anyway, and put them on Hubble diagram even further out. And we think we'll get better than a 2% measurement of W, which is somewhat better than what we get now, and hopefully get some constraints on W0 and WA. But with a nice uniform homogeneous sample with very large numbers where we can really look at these astrophysical effects as well.
So I had a question. So for the target selection for foremost, do you need Rubin at all, or can you select the targets from the archival images that we already have from DCAM and DCALS and DES?
There won't be enough, I don't think. I mean, we could certainly do the host galaxies of those. I'm quite interested in that.
But in general, not for the piggybacking section of the supernova, but for the foremost main survey, are they going to be relying on previous to Rubin images, or are they going to rely on targets selected from Rubin?
It will be Rubin. Once Rubin's running, it will. But unfortunately, I think there'll be a period before Rubin is available when Foremost is. I should have put the date. So we're expecting Foremost to be starting end of 2024. Which is a bit early for Rubin, probably, because Rubin takes time to build up its reference images and everything. So we will be looking at things like, DECAM surveys, and that's one of the reasons I'm on these trips. It's very useful for us to be able to get some targets to start off with, to get a lot of the mechanism running, and it should be useful the other way around as well, because we can provide redshifts and types.
Isn't that going to complicate your selection effect?
Yes, I probably won't be usable as the main survey, but it will be very useful for getting things going. I think there's going to be a lot of teething problems to iron out as things go on. Right, so I thought I'm going to spend a little bit of time talking about some of the things we're doing in Lancaster. There's obviously a lot of projects you can imagine doing with Foremost. Most of this is simulations, of course. We don't have real data. But we've looked into various things. One of them I'm not going to talk about, but I'll just mention here, is this issue of being able to train photometric classifiers using the TiDES spectroscopy for a subset. So John Carrick, who was a graduate student with me, who's now finished, has written this up, and it's very nice, actually. So what he showed was that, first of all, there is a bit of a problem, because TiDES has this 22.5 magnitude flux limit, which is quite bright. And it means that most of if you use that as a training sample to try and classify all the much fainter Rubin transients, it doesn't do very well at all, because it just doesn't know what to do with the fainter objects. And what he showed was that first of all, he showed that problem and then showed that you can use data augmentation to kind of simulate what the other objects should be, just based on no assumptions about what they are, but simply taking the ones you've got, the brighter ones, and artificially redshifting them and dimming them based on, you have to assume a cosmological model, so that is a slight problem, but that works incredibly well, actually, for the training. So that's all I'm going to be able to say about that, I think, unless anyone wants to talk about it later. I've mentioned the simulations that Chris Frohmeyer has been doing on the statistics of the objects we're going to get and the cosmology. But I want to focus a bit on what we're doing with the host galaxy properties, which is work being done by my student, Jamie Dumain. And again, we're hoping to use the host spectral information to help with the photometric classification. So I'll show a bit about that. And the other thing we're kind of worrying about is how we're going to actually classify the spectra that we get off TiDES, the live spectra. We've still got to classify those. And in the past, we've looked at spectra by eye. A human has looked at them all and said, yes, that's a type 1a and that one isn't. We're not going to be able to do that. So we're going to have some automated system. And that's what I'll talk a bit about that later. So starting with the host galaxy properties. So this is work done by Jamie Dumain. So the idea here was that we thought that by, every time we get a host galaxy spectrum, we're not just going to get a redshift, we'll get information about the stellar population in the galaxy and lots of other information as well. And we're wondering, could we use that to help us measure the mass of the galaxy? So that could perhaps be useful in the mass step correction that we need for cosmology. And also it could help with transient classification, because we know that different types of transients explode in different types of galaxies. So that was the general idea. So we set out to generating simulations. And so what Jamie did was take one galaxy, a template spectrum, and shift it to different redshifts and magnitudes. And then for each one, calculate the photometry you'd get from LSST's 10-year depth. So that's these red points shown here, assuming this filter responses. And what sort of spectrum would you get from foremost? So he ran that through the foremost exposure time calculator. And that's the cyan-colored spectrum here. And you also get a noise spectrum from this exposure time calculator. So you know how much noise there should be on that spectrum. And then what he tried, so that now he's got a big set of these simulated spectra and photometry. And then he tried to run those through spectral energy density fitting codes. And we chose the FAST code. So this is there are lots of these types of codes around, and you may well have your own particular favorite, but we like this one because you could use it both on photometry and a spectrum. And what it does is you give it this data, and it tells you what it thinks. It matches it to a library of different galaxy templates and tells you what the best match galaxy is and what its stellar mass is, its age, its star formation history, metallicity, and dust attenuation. All of these parameters come out with uncertainties, and a lot of them are correlated uncertainties. So that's what we tried to do. So what's shown here is the, if I get this the right way around, so this is the fit to the photometry. So this is a fit now, not the input spectrum. This is a fit to the photometry and the spectrum, shown in yellow. And this is the difference between the two fits. So this is showing you how much information is the spectrum changing, is adding to the fit. So you can see there are some subtle differences there, and those change the output mass and so on that you get out of the code. We also know the truth for our input galaxy, because we ran that through FAST as well. So we know that's actually what we used in the end. We took our input galaxy, ran it once through FAST, so we've got its mass and everything, took that best fit, and that became our template. So we actually know the truth in one case. And then we compare the results. So this is what we got for stellar mass. So this is a plot of stellar mass output from these fits against the magnitude of the galaxy. And you can see there's this strong relation. That's just because FAST basically uses the brightness to give you a stellar mass. But what's interesting is the size of the uncertainties here. So what we're finding is that basically at every magnitude that we sampled, the photometry is shown in the orange error bars here. Those uncertainties are larger than you get when you add in the spectroscopic information, which isn't surprising. You would expect it to help, but this quantifies how much it helps. And basically, every redshift and every magnitude that we looked at, it helps, and we can say by how much. So we've quantified this improvement. Then we tried seeing what that does to our cosmology, particularly towards the mass step. And it turns out the effect is absolutely tiny and basically negligible, which is a bit disappointing. I think so what's really happening is it very slightly improves the mass measurement for every object. And in some cases, that might move the object from one side of that line, the vertical line that I showed you on the plot for color. There's a similar one for mass. So occasionally it moves an object from one side to the other, but it moves some the other way. And really, it doesn't actually make a big systematic difference. It very slightly it improves the uncertainty on W, but it doesn't really affect the actual value in any systematic way. So that was a null result, but moving on, we then looked at what does it do about, does this information help with transient classification? And there it's, I think, a bit more visible what happens. I'll show you that in just a minute, but I did want to mention that one of the things we found was when we look at the age of the galaxy that comes out of this fitting, the spectroscopy really helps a lot there. So the error bars are quite significantly smaller. So if it turns out that age is the parameter that is actually driving some of these correlations with the brightness of the supernova, then we're in business, because then we can get quite a lot of information out of that from Foremost. But we don't know yet, and I think this is going to be really interesting when we start doing this for real. Right, so just going back to the photometric classification. So, as I said before, we know that supernovae of different types prefer different types of host galaxies. So the question was, can we use these improved host galaxy parameters that we're going to get from TiDES to help with the photometric classification of all these supernovae that we don't get live spectra of? So we set out to answer this using a machine learning approach where we just add extra information to the training sample. And in this case, our extra information is the host galaxy properties, and we are using the kind of physical host parameter properties that we get out of this fitting. So what we did was start with the same simulations that I showed you before from Chris Frohmeyer, which includes simulated light curves. I should have put an example light curve, but you've probably seen them where the light goes up and down in different filters. So you get color information there, which helps with the classification. And then we added in various bits of extra information to the training sample and see how it performs on a test sample. For all this, we're using the Supernova deep neural network from Anais Muller et al. For our classification code. And I've said, so we add in various things. So we add in various steps a redshift, which we will get from TiDES, stellar mass, which we'll get from a fit to a TiDES spectrum, star formation rate, and that's where we stopped. We didn't try adding in anything else at this stage. But the main reason for that is because those are the only things that are actually included as correlations in the simulations. So there's not much point adding the other things in at this stage. But with real data, we don't know what's going to matter, so that'll be very interesting. So these are the results from this test. So we're using precision as our metric, and it's defined here, the true positive rate over the true positives plus false positives. And I think if I've got this right, you can think of that as 1 minus the contamination rate. So typically for supernova samples for cosmology, we want a contamination rate less than sort of 5%-ish. We can just about cope with something like that. Right, so what we've got here are various amounts of information being added in. So the bottom one is light curve information only, no information about redshifts or anything like that. It already does pretty well, actually. It's already doing better than the 5% kind of nominal contamination. If you add in a photo Z with what you expect the uncertainties to be, it improves a bit. But adding in a spectroscopic redshift really helps quite a lot, quite noticeably. So just by adding redshifts, I think that will help quite a lot. And that makes sense because it obviously constrains the type of object that it could be from its light curve if you know the redshift. Then we tried going going back a step to photometric redshifts, but adding in some photometric host information. So if you didn't have TiDES at all, just the Rubin information, we go back to here, and it's actually slightly worse than light curves only. And we think probably what's happening there, I mean, it's not really significantly worse, but it's probably just that the information we've been adding in here includes very poorly constrained star formation rates, some of which just hit the limits of -99 that FAST spits out. So it's probably just confusing it, actually making it slightly worse. But if you now go back to spectroscopic redshifts and spectroscopic host information, there's quite a big increase again, a bit better than just redshifts. Redshifts seem to be the most significant jump, but redshifts and host galaxy information gets you a bit more improvement. And then at the top is if you had that information with no uncertainties at all. So just using the simulated truth, that's the best you can do. So we're actually not far at all off there. So that's quite interesting, I think. This is very preliminary. We're still looking into this, but yeah.
When you're talking about perfect host, it means that you have like a very good characterization of the host galaxy in terms of like the acidity fitting and, you know, the star formation. Is that what perfect means?
Perfect means, no, it's the simulated value that went into the simulation. So in Chris's simulations, he associates a host galaxy with every supernova, and that host galaxy has a modeled mass and star formation rate. And then they do some correlations to map, to decide which supernovae go in which galaxies. So there's a bit of uncertainty there, but the actual properties of the host galaxies have no uncertainties on them.
Sure, but I guess what you're trying to, I'm trying to see if I get this right. So the message that you're trying to say is that not only getting the spectroscopic redshift is important, it's also very important to characterize the host galaxy and their properties in order to understand the progenitors of the supernova, so you actually get the right one and you don't get the contamination. And in principle, that's what you're going to get if you have a good acidity fitting and you have good photometry and you have the combination of both.
That's right.
Okay.
Yes, that's right.
If you would have asked me a priori what this would look like, I would assume that having a light curve only would be useless. A photo Z would get you most of the way there, and then spec Z would be kind of like epsilon on top of that.
It is surprising that it does this well. I mean, some others have used this a lot.
Photo Z is good to 10%, 5%.
But not for the acidity fitting. I think that the acidity fitting has like ton of uncertainty and until you get the right, because there are too many degeneracies.
But
we're talking about this jump.
Yeah, but that
here.
jump has no acidity fitting, right? It's just distance.
Yeah, it is rather surprising. I guess it's just learning very well, I guess, what these light
I think the thing people don't appreciate is that type 1a light curves also give you a photo Z intrinsically because there's time dilation and they're the same length. So there is actually a photo Z constraint even in the thing. But what's maybe deceptive a little bit here, if you're not catching it, is that the sample size, I think, is constant all the way up.
Yes, thank you. Yeah.
But in reality, we have, I think, 100,000 objects that are light curve only, and Isobel mentioned something like 31,000 odd. So factor of 3 maybe in size. And the question is, how much better do you do on W dot by having a smaller factor of 3 sample, but maybe cleaner systematics?
Yeah, that's an excellent point. Yes. Yeah. Yeah, and I don't think we're going to, not in this work, we haven't got to the point of taking it through to the next step, and that would be really interesting. Yeah. Okay, so where have I got to? I want to get to Euclid quickly before I finish. This is just very briefly, I want to mention this. So we've got this other issue. We're going to get live spectra from TiDES, and we need to classify them. So another bit of work that we're doing now is trying to work out which of these classification codes should we use, and what level of performance can we expect. And to do this, we've been making blended spectra, because most of the TiDES spectra that we get of live transients will also have host galaxy light down the fiber as well. And so we're interested to see how well we can do with these blended spectra. My student, Andrew Milligan, has been doing this work, again, doing a massive simulation based on Chris Frohmeyer's input simulation, taking all the supernovae and all the galaxies they're associated with, and working out how much light goes down the fiber for each of these combinations. And then he runs that through the foremost exposure time calculator for each one and generates a noisy spectrum, realistic noisy spectrum, and then we try and classify that. So these are the steps that he's taken So for each supernova, he works out, that'll be basically a point source, he works out how much of the light makes it down a fiber and how much is lost, and then does the same for the host galaxy, where we've in the simulation, there's a distance from the center of the host galaxy and some profile information about the host galaxy. And so he can calculate how much light gets down the fiber, generate the combined spectrum and add noise to it. And this is the sort of thing we get. So you can see supernova features in there, but there's noise and there's a kind of offset from the host galaxy as well. And then try running it through 3 well-known spectral classification codes called DASH, NGSF, Next Generation Superfit, and SNID, which are all often used in the community, and sees how they do. And they've all got pros and cons. Some of them really struggle, some do better, some really need a redshift, and that helps a lot. Some don't mind too much. And so this is all very much work in progress, but this is the sort of comparison he's been doing. So maybe if we, I don't know, look at the top one, which is the rate of real type 1a supernovae that get correctly classified, you can start doing comparisons. And this is done as a function of exposure time, because that's another thing we're worrying about at the moment. So for example, DASH with a known redshift does very well. If it doesn't have a redshift, it does much, much worse. And it just basically classifies everything as a type 1a, which is why you get a very low false positive rate, which is, if you consider a positive to be a 1a, that is. So anyway, I won't go into much detail there, because that's still very much work in progress, but just to show you the sorts of things we're doing. Right, so so the next thing will be to decide what quality cuts we want to apply, and that will become our standard when TiDES is running in real time. So that's really where that work's going. Okay, right, finally, I've just a few more minutes. I want to get on to Euclid, because there's a lot happening there, as you can imagine. So Euclid is an ESA mission with NASA participation that was launched in July. I got to go, so that's my photo of the launch. It's quite a small telescope, 1.2 meter telescope, but the main thing is that it has very wide field cameras. So it has about half a square degree per pointing. In optical, there's an optical camera and a separate near-infrared camera, and the near-infrared camera also has a spectrograph, a slitless spectroscopy. And so this is going to carry out a survey of the whole extragalactic sky, or a very large fraction of it anyway, and also to do some deep surveys. And I think I've got a plot of the survey. Yeah, so on the same sort of plot, the green areas are where Euclid, in one of its realizations of its survey, is going to look. So there's quite a big exclusion zone around the galactic plane, but very large sections of extragalactic sky covered there, but quite a lot in the north, which unfortunately won't overlap with Rubin or Foremost. So the main goals of Euclid are weak lensing and baryon acoustic oscillations. So the weak lensing part means we have really excellent image quality, and that's really nice for lots of other reasons as well. So the first images have started coming down. These are some of the commissioning images, which have had basically no fancy processing done on them at all. So this is an image from the VIS instrument, which has 36 CCDs arranged in a 6x6 pattern, and that's a zoom in. So you can see some strange artifacts. It looks like there's a ghost there, and you see, when you look at these in more detail, you see a lot of cosmic rays. So that's been an issue that was a higher rate of cosmic rays than were expected. And you may have heard that actually also has had quite a big effect on the fine guiding sensing. In fact, worse than that. I mean, it was really quite bad at one point, where it couldn't lock on at all and was just wobbling all over the place. They've sorted that out now, and I think we have really nice guiding. So they're now back on track, so that did cause a bit of a delay. So that's the visible imager. This is the near-infrared instrument, same field of view, but a bit more, slightly larger gaps between the detectors. And that's another zoom in. Again, very nice imaging there. And that came out straight away. So the image quality is excellent. When the guiding is working, it's really, really nice. And this is the slitless spectroscopy image. A huge amount of information there, and you can imagine that there's going to be quite a challenge to disentangle all these overlapping spectra. So one of the things Euclid does is rotates when it's observing the same field, so that it can disentangle these by taking spectra at different orientations. So transients in Euclid, this has been quite a long story, and the basic problem. I mean, a lot of people would just assume or tell you there isn't any transient science with Euclid, and it has been quite a battle to get anywhere with this. Perhaps I shouldn't say it like that, but the basic problem is that the Euclid baseline survey is not designed for transients at all. The Euclid, for most of the sky, will only visit once, and it's only in the deep fields, really, where there will be repeat observations. And even those have quite a large separation. So, for example, this is a plot from a paper by Cosmo and Sarah, who was interested in finding superluminous supernovae with Euclid. And this shows that 3 of the deep fields with time when the visits happen. And this is 6 months. So a 6-month gap is much too long for finding a type 1a supernova, which has a timescale of a few weeks. But there are some places where there are actually within each of these visits there are some multiple visits of the same field, but they tend to be a bit too close together. And again, we don't have any control over this, so we just have to take what we're given. We did do a study quite a few years ago about what could Euclid do if you could control when it looked. And there's a very nice paper that Pierre Astier wrote about this. If you took 6 months of Euclid time and did a dedicated Euclid supernova search, it would be amazing. We'd get to about a redshift 1.5 with very nice cosmological constraints. It's still possible that could happen if there's time left over in Euclid's survey, so we don't know yet. We'll see whether that happens. So what we've been thinking about anyway is what can we do with the main survey. We can do long-duration bright transients like superluminous supernovae, possibly pair instability supernovae. So there's a paper out about how Euclid would perform there. Again, this is mostly in the deep fields. And you can do some cosmology because you will get, again, in synergy with Rubin, we think we'll get actually thousands of kind of single or a few points, near-infrared points, on optical light curves. So in conjunction with Rubin, it will be very nice. And there's a paper by Ava Bailey about that. I think one of the most interesting things is actually all the amazing information we'll get on the host galaxies, because we'll get almost HST resolution imaging of all over the sky. So we're going to have fantastic information in the near-infrared and optical of the host galaxies. Right, I'll skip that. So one of the exciting things that's happened recently, though, is that it was noticed that in the performance verification of Euclid, it will be going back to the same field of sky quite often. And this is called the self-cal field. So it's visiting this field to do some calibration steps. But by doing that, it's going to give us some data that could be useful for transients. And it might actually be the best set we get for quite a while. So this is a 3 square degree calibration field near the north ecliptic pole. And this is a map of it here. It's this red region here. It's going to be observed 6 times in the first 8 weeks after launch. So this is very early, and this is one of the issues that a lot of the basic mechanism for Euclid's, both the observations and the data reduction, isn't in place yet. So it's happening right now, but it's hard work. So this is really exciting, though. And so after it's done that, it will also keep going back to this field roughly monthly. So we've started looking at what we might be able to get out of this with some calculations. So what I'm going to show you in a minute is what we would expect from what we call a short survey, which is this first 6 visits in 8 weeks, and then a longer survey with visits once a month for 4 years. So these are the numbers. I'll just put the whole lot up for now. There we go. So the short survey, we think we'll get 25 supernovae of all types, of which 6 will be at redshift above 1. So that's quite a nice little survey just to see how things work. And we'll get, sorry, those are all type 1a, sorry. It's 25 type 1a supernovae, of which 6 at redshift 1, 29 other types, of which 4 at redshift above 1. So altogether, we'll have about 10 redshift above 1 supernovae just from those first few weeks, we hope. And then the long survey, we'll have, this is the long monthly visit type thing, we'll get about 500 supernovae above redshift 1, but with just 1 detection. And possibly 10 superluminous supernovae, and we don't know the rates of pair instability supernovae at all, but possibly something between 2 and 20 of those, maybe even up to redshift 5. How we'll know what they are, I don't know. That's another issue, but we might detect them. So this is work that Enrico Capellaro and Takashi Maria have been doing. to make predictions. So basically, it looks interesting, and I think we've got a chance of finding.
When it comes back to the self-cal field, when you say it's only one detection, are they not actually doing the entire slew of filters and the GRISM mode?
Yes, they will do that, but it will all be done in one go. So it will be, there won't be more than one epoch. Perhaps I should have put it that way. So it'll be more than one detection, so we'll check. That's true. Yeah, we'll know it's not a cosmic ray or something, but we won't have more than one epoch together.
And how large is the full Euclid field of view, out of curiosity again?
Sorry, say again?
How large is the field of view for Euclid?
0.5, well, for the self-cal field, it's 3 square degrees. So if it does the whole 3 square degrees, these are the numbers we get.
Advanced us is 7 square degrees. And we can keep hitting it with enough.
At the same time, yeah. Well, this is the thing, we'd really like to do this, coordinate these observations with optical going on at the same time, if we can get the schedule in advance.
Can you do cosmology with these? Like, do you have a light curve?
Probably not.
Yeah, okay.
Well, unless we do, as Gautam's suggesting, if you could do simultaneous optical photometry, yes, you could. You'd also have to get you'd have to get a trigger in real time and get a spectrum, ideally. But yeah, and it's something we're thinking about with Subaru. So it's in the north. It would have to be, yeah. We'll talk about that later. Good. Right. Well, I've got about 2 more slides, I think. So we before Euclid was launched, we did some simulations on image subtraction using simulated pre-processed data. And of course, it comes out really clean, lovely simulations, and we were all very excited. And then we got the real data, and it's much harder. Surprise, surprise. Particularly because the pre-processing is not running yet. So we are starting from raw data, and there's quite a few effects, particularly the near-infrared detectors have quite a strong persistence problem. So a lot of the sources we find are on the cores of galaxies and probably just a persistence effect. But so that's going to be quite difficult to deal with, I think. So the latest news on transients, so we have actually found a transient. We're not allowed to show it to you because there's going to be a big press release in November for all of Euclid's start of operations sort of splash, and it's possible it'll be included in that. But we have found one. It wasn't actually in the self-cal field, and it wasn't found by the transients group. It was found by people who are looking at comparing Euclid data with other data at other wavelengths and other facilities. And they spotted something that looks like a supernova and found that it wasn't in another image. So we have actually managed to do follow-up of that and shown that it is a supernova. So that's a nice demonstration, but it's not going to be much use for cosmology or anything. Meanwhile, the self-cal search has started, but in a very minimal way. So before the PV phase that I mentioned, the commissioning itself also looked at one field in self-cal. So this is half a square degree. And we've got 2 epochs of that data and a third just coming with half a square degree. So we're really just starting now, trying to do subtractions on basically raw data. And it's quite hard work, but we're getting there. And this is focusing mainly on the near-infrared. Yeah, and as I say, it's quite hard work. So what our expectation is that this self-cal field will be a very good test case. We'll be able to get things like basic transient rates and rates of infrared detections from that, and then hopefully scale everything up to larger scale when these deep fields are running, and potentially even a dedicated survey if things look good from these earlier tests. So that's it. I think we're really pushing the current telescopes to their limits at the moment, but we've got this amazing suite of things coming, and we're going to have an incredible overload of data, really. Better statistics, we'll be able to control systematics and extend to higher redshift, and hopefully test the properties of dark energy, but we will see. So I'll stop there. Thank you.
Questions?
So I might have missed this, Isobel, but when you talked about the Foremost program, how are you getting the host galaxy spectra? Are you having to come back weeks or months later, or you think there's a fiber you can put that excludes the transient and just gets the host galaxy?
Yeah, that's a really good question. So they're actually not going to be the same objects that we get the live transients for, the live spectra. So typically we'll get a live spectrum of everything in the field, and the host ones for the hosts for old supernovae, but they won't be the same objects. So we won't be able to come back. what we could possibly do is at the end of when Foremost is finished, maybe we put in a separate proposal to come back and get host galaxy spectra for all the ones that we got the live spectrum for. But that is a bit of a problem, actually.
Oh, so there's no guarantee you can go back. It really depends on the sequence of fields.
Yeah, some fields we will. So the deep fields we will. Okay. But for the main wide survey, generally we won't, unless just depending on whether another survey wants to go back for some other reason. Then we might be lucky.
Alex, I see your hand online on Zoom.
Yeah, hi, wonderful talk. It's really exciting research. I wanted to ask, so you mentioned with Jamie's work, you were mainly looking at the redshift, stellar mass, and star formation rate of the host galaxy because that's what you simulated. I was wondering, in practice, if you have thoughts about additional properties that might be useful for doing this kind of photometric classification, whether an image would get you a little bit further, or whether the entire spectrum would push you toward higher purities. Do you have thoughts on that?
Yeah, that's a good idea. Yes, the whole spectrum, just put the whole thing in somehow into the machine learning. Yeah. No, I haven't really. I mean, I think one of the first things we'll do as soon as we get real data is start looking for correlations between properties and rates and between properties and the brightness of type 1a supernovae. Both of those are really interesting. I don't know what we're going to find. But yeah, no, we haven't really thought much more about it than that, really. We'll wait for the real data.
Yeah, thanks very much.
Thank you.
Other questions?
How are you deciding which supernova to get spectra of? Is it just whatever's active in the sky, or are you following, say, whatever gets posted to TiDES and like you have some idea of what you're looking for?
Thank you. Yeah. Well, for mostly we'll just take everything certainly everything that comes from Rubin down to this flux limit, because I think we're not limited by the number of fibers. We've got too many fibers really. The limit is our 22.5 magnitude limit. So the basic criterion will just be anything that's going up that's more than, I think we've got a criterion about how many times it's been detected. It's got to be detected on more than one epoch and in more than one filter, but otherwise if it's brighter than 22.5, we'll have a go. And then there are ideas to get other data streams. So one idea actually we've been talking about a bit here is that there are other ways of selecting targets, like for example this respect idea where you pick a particular object that would be particularly powerful for machine learning to train classification of the other objects. So there may be other streams coming in, and maybe some of the other facilities that you mentioned, we could put them all in. I mean, I don't think there's going to be too many, as long as they've got a flag that says where they've come from, and so we know our selection function. I think we can probably manage many other streams as well.
Maybe I'll ask one quick question. You didn't talk about the fibers themselves. Are they all high resolution, low resolution? Is there a mix?
There's a mix, yes. So it's 2/3 are low resolution and 1/3 are high resolution.
And what are the sort of fiber positioner constraints if you find a neutron zone?
There is, I think the only constraint is that you can't have two fibers closer than about 6 arc seconds.
Oh, that's not bad at all. All right.
I'll have to look that up.
Okay.
Yeah. But it does mean you couldn't do a supernova and, well, you may not be able to do a supernova and a host simultaneously. Yeah.
I think that's a little easier than DESI though. So. Other questions for Isobel? Okay.
I didn't catch the wavelength range of TiDES.
Yes, it's optical. It's sort of, it's about 4,000 to, let's see if I've just got an example spectrum somewhere. How do I get out of here? It's optical, and it is actually quite high resolution. Even the low resolution fibers there's one. So whatever that is. Yeah, I should have put that on a slide. So it was, 4,000 to 9,000 roughly. Yeah.
Thanks.
What's the status of the spectrometer, and where is it being commissioned?
It's currently in Potsdam in Germany, and it's pretty much ready to go. It's going to be shipped by the end of this year, and it should be commissioned in Chile. It's going on the Vista telescope which is near Paranel in Chile. And that should happen, the commissioning should be happening in sort of spring and summer. And then the survey will start at the end of the year, we hope.
Patrick, maybe we'll end with you.
Sounds good. Can you give a guess on what percentage or fraction of the supernova spectra will be classified by these automated algorithms, like some kind of ensemble dash and SNID versus like human, and how would that play into like?
Yeah, this is exactly what we're worrying about now. I think it might be quite a low fraction actually that can be automated. From what we're seeing now, well, I think perhaps the next slide even. Yeah, I mean, so the best ones are getting, well, it's not quite the right metric, but around 80% right for 1As, but you obviously want everything. So there's going to be an awful lot that are going to need looking at, I think. But that's something we're working on. And you know, one of the really nice things would be to put other information in. This is just purely from the spectrum, but we will know other things about the light curve and the photometry of the host. That might actually help us with the spectral classification as well and give us one overall classification. But we're nowhere near ready for that yet.